Welcome to Ask and Learn.
In this problem, let's see here, we have a facility where we have a bunch of brass plates that are being heated as they pass through an oven. And we're told that they pass through at 175 plates per minute. And we're told that they need to stay in the oven until their average temperature rises to 1,000 degrees Fahrenheit, and determine the rate of heat transfer to the plates in the furnace and the rate of exergy destruction associated with the heat transfer process. Okay, so these are brass. So we can look up the density of brass and the heat capacity of brass. So again, the heat capacity is low, which is good because they'll absorb the heat quickly. Or they'll absorb. Things will go kind of in our favor here. We want them in the end to be 1,000 degrees Fahrenheit. So again, I forgot to write my little notes here. So we have degrees Fahrenheit, pound mass, BTU, and then feet will be our length unit here. All right, so they're initially at 75. Okay, so initially T1 is 75 degrees Fahrenheit. And the oven is 1,300 degrees Fahrenheit. So we can figure out the mass of each one of these brass plates. This is the volume. So we were given all of the dimensions of them. So we can figure out the volume, multiply by the density, and we find out that they weigh very close to 200 pound mass each. So then we can turn our attention to the heat transfer that's going into each one. So we know their mass, we know the heat capacity, and we know the change in temperature. So we know the heat going in is about 17,000 BTU per plate. So we have, let's see here, also we have units of seconds in this problem as default. So we have this much BTU per plate. We know, now we want to find the total heat transfer that's going in as a function of time to these plates as they move through. So we know that the rate of flow of plates, I'll call it N dot, and that is 175 plates per minute, converting that to seconds. So we divide by 60, and then we know how much heat needs to go in per plate. So we wind up with about 49,000 BTU per second of heat is going into these plates as they move on through. So again, this thing here is, this rack is basically traveling. Again, we're not told any dimensions of kind of this furnace or anything, so we really don't know the rate of this. We just know that they're going through, at this rate. So when they come in, basically you can just count them as they go in, and then obviously they're coming out. So it's kind of a mass flow rate. I mean, you could really think of it as a mass flow rate, basically, because we have the mass of a plate. So this would be kilograms per plate, and we multiply it by this, and we get kilograms per minute of copper or brass that's throwing in here. So now we turn our attention to entropy. So the entropy in minus the entropy out plus the entropy generated is the change in entropy in the system. The entropy is basically just this entropy here is just, we're going to assume is from the heat, well, not assume, the entropy in and out is just from the heat transfer. Okay, so the entropy generated is the entropy generated from the heat transfer, well, minus that, depending on what we assign here, plus the change in energy in the copper plates. And we can figure that out by, well, that's just their mass times each copper plate's change in entropy. And again, we can, because they're basically solids, we can use the heat capacity and the natural log of the temperature difference, or temperature change, temperature ratio of temperatures. Um, and again, this was going to be the average because this does change with temperature. So as it goes from pretty cool room temperature to 1,000 degrees Fahrenheit, this thing is going to change. But again, we're taking average values. As specifically noted it here. I probably should have said it, specifically noted it here and also here. Now, let's see here. We know everything. We know all these values now. So we can figure out that the change in entropy, and this would be the change in entropy per plate, is 18.24 BTU per pound mass Rankine. So, plug that into here because we have a heat transfer per plate. And we know the reservoir temperature. And so we wind up with a entropy generated of about 8.69 BTU per pound mass Rankine per plate. Again, we can multiply by the flow rate of, the number flow rate of the plates. And we get then that we get a total entropy. The rate of entropy generated is 25.35 BTU per pound mass per BT 25.35 BTU per second per Rankine. And so the exergy destroyed is just the surrounding temperature, which again, did I not write that down? I think we just used 75, right? I used just 75. Yeah. So this is also T naught. So 75 converted to Rankine, of course. And so then we get the rate of exergy destruction is 13,560 BTU per second. So again, we could be getting, we could be putting little heat engines on these plates and then try to grab some energy as the heat flowed in from the surroundings into these plates. Well, that seems like it would be not a very feasible or reasonable thing to do. So again, we're probably just going to have to deal with this and just say, well, it's a loss, and we're not going to be able to, that's what's going to have to happen because we're not going to attach heat engines to each one of these plates.